All around us, there's this invisible world of pushes and pulls that's deciding, well, pretty much everything. From the way a basketball spins to the incredible power of a thunderstorm, it's all run by forces. In this explainer, we're going to pull back that curtain. Let's dive in.
Okay, so take a look at this. It's a classic scene, right? Two dogs, one rope, and a whole lot of determination. Each one is pulling as hard as it can in the opposite direction. The big question is, who's going to win? By the end of this, you'll know exactly how to figure that out, not just for them, but for any battle of strength.
So, to predict our winner, we've got to get the science down first. It all really boils down to one super basic question. What exactly is a force?
In the world of science, it's actually pretty simple. A force is just a push or a pull. That's it. But here's the really important part. Every single force has two things going for it: a strength, how strong it is, and a direction. And those two ingredients are what make forces run our world.
So, what can these forces actually do? Well, for one, they can change an object's shape. And what's just mind-blowing about this picture is that squish. That golf club is moving at nearly 45 meters per second, and the force of that impact completely flattens the ball for a split second. That is a powerful push, changing an object's form.
And second, and this is the one you see all the time, forces change motion. Seriously, anytime you see something speed up, slow down, or just change direction, you can bet a force is behind it. This backhoe isn't just sitting there with some rocks. It's applying a huge force to push and lift them, changing them from perfectly still to, well, not so still.
So how do we measure the strength of all these pushes and pulls? Well, scientists use a special unit called the Newton, and it's abbreviated with a capital N. So from now on, when we talk about how strong a force is, we're going to be talking in newtons.
Okay, now here's where things get really interesting. See, in the real world, it's almost never just one single force acting on something. Usually, an object is caught in a battle between a bunch of different forces. And this fight can only have one of two outcomes. It's either balanced or it's unbalanced.
On the left, you've got balanced forces. A perfect example is a house of cards. Gravity's pulling it down, sure, but the table is pushing up with the exact same amount of force. They cancel each other out, and what's the result? Stability, no change in motion. But on the right, you've got unbalanced forces. When a skater pushes off a wall, that force isn't being canceled out by anything. It's unbalanced, and it causes a change. She speeds up and moves away. And this is the bottom line, the thing you have to remember. Only unbalanced forces cause a change in an object's motion.
Okay, so if everything is in this constant tug of war between different forces, how in the world do we figure out who wins? Well, we need a way to add up all the pushes and all the pulls to find out the final result, and that final result has a name. It's called the net force.
The net force is basically what it sounds like. It's the grand total, the overall force that's left after you combine all the other forces acting on an object. It's the final verdict. It's what tells you if something is going to move, and if it does, which way it's going to go.
And the best part? Figuring it out is actually super simple. There are really just two rules you need to know. Rule number one, if forces are pointing in the same direction, you just add them together. They're working as a team. And rule number two, if forces are pointing in opposite directions, you subtract them. They're fighting each other.
Let's see it in action. Here we've got two people pushing a box, and they're both pushing in the same direction. One's pushing with 30 newtons, the other with 20. Since they're on the same team, we just add them up. Boom. The net force is a strong 50 newtons to the right. But what if they're working against each other? Now, the person on the left is still pushing with 30 newtons, but the person on the right is pushing back with 20. We subtract the smaller force from the bigger one. So 30 minus 20 leaves us with a net force of only 10 newtons to the right. And this shows you the single most important rule of this whole thing. When the forces are unbalanced, the object will always move in the direction of the stronger force, period. The bigger force always wins the fight.
So, this brings us all the way back to our dogs. The winner of the tug of war is just the dog that can pull with more newtons of force. That's it. That dog creates an unbalanced net force in its direction, and the rope and the other dog get pulled its way. It's all about the net force.
All right, now that we've got the basics down, let's take all this knowledge and apply it to something, well, a little more exciting. A roller coaster. Let's see how all these ideas of balanced and unbalanced forces come together in one heck of a ride.
Think about it. When you're on a roller coaster, you are the object at the center of this huge, epic battle of forces. You've got gravity constantly pulling you down.
You've got the seat pushing you up. As the train rockets forward, it's pushing you back into your seat. And, maybe most importantly, you have those restraints applying forces to make sure you don't go flying out.
And you better believe engineers have to calculate these forces perfectly. This chart kind of shows you how they think about it. For a gentle little coaster with small hills, a simple lap bar is going to be fine. But if you're going upside down through loops and crazy inversions, no way. You're going to need that heavy-duty, over-the-shoulder restraint to provide the strong force you need to stay safe. Each restraint is designed to create a very specific net force on your body.
So you see, it doesn't matter if we're talking about a simple game between two dogs or the super complex engineering of a giant roller coaster. The principle is exactly the same. Every single change in motion, every single time something speeds up or turns, it's just the result of the winning side in a constant battle of forces.
And that, of course, brings us right back to you, right now. As you're sitting or standing there, what invisible forces are deciding your motion? Gravity is pulling you down, your chair or the floor is pushing you up. Right now, they're probably balanced. But what happens if you decide to stand up? The world of forces isn't just in a science book. It's deciding your every move. What are you going to notice next?